Welcome to a new session on the massive open online course Introductory Concepts of Digital Computing offered by SWAYAM. This session focuses on combinational circuits, in particular adders. From the previous sessions, we acquired some basic knowledge about binary arithmetic, Boolean algebra and basic logic gates. We have studied how to express logical functions using Boolean algebra, then how to minimize Boolean functions and the realization of Boolean expressions to efficient logic circuits. During this session, we shall use these concepts to design combinational logic circuits. Logic circuits in digital systems may be combinational or sequential. This session deals with combinational circuits. What is a combinational logic circuit? These are digital circuits that has no memory and its output at any moment depends on only its present inputs. The memory element is used in sequential circuits, which we will discuss in a later session. We had already designed some logic circuits when we studied about logic gates. All those circuits were combinational circuits. A combinational circuit consists of input variables, logic gates and output variables. In a combinational circuit, a set of logic gates or a combination of logic gates transform input signal into a set of desired output signals. So, it is said that logic gates are the basic building blocks of combinational circuits. Depends on the Boolean expression, a combinational circuit may take n inputs and m outputs. Refer the block diagram shown here. N inputs are passed through a combinational circuit to obtain m outputs. These m outputs are solely depending on the value of n inputs. For n input variables, there will be 2 raised to n combinations of binary input values. And for each of the output, there will be a corresponding logic function in terms of the input variables. And the combinational circuit is always described by the combinations of these output functions. Let me introduce you one of the simpler and most useful combinational circuit. It is based on binary addition and the circuit is adder. Based on number of input bits to the adder, we can classify them as half adder and full adder. First, we shall see what is a half adder. Before that, let us recall the basic rules of binary addition. 0 plus 0 equal to 0, 0 plus 1 equal to 1, 1 plus 0 equal to 1 and 1 plus 1 equal to 0 with a carry of 1. These basic operations are performed using the logic circuit half adder. The half adder accepts 2 binary digits on its inputs and produces 2 binary digits on its outputs, and those outputs are sum and carry. To perform addition on 2 binary numbers, what do we do first? Adding LSBs of those numbers. What it generates? Sum of these bits. If the sum exceeds 1 bit, the extra bit will be added to the next set of bits on the left side, and we call this bit a carry, right. So, addition of 2 bits, just 2 bits has 2 outputs, a sum and a carry. Okay. Here shows the logical symbol of a half adder. A, B are 2 binary inputs and sum and carry are the outputs. Good. Now, let me describe the logical operation of a half adder. For that, let us write the truth table of half adder. The input variables A and B take the values 0, 0, 0, 1, 1, 0 and 1, 1. Write the output 0, 0, 1, 0, 1, 0 and for the last case 0 and carry 1. From the truth table, we gather some facts that A and B are the inputs to half adder and sum and carry are the outputs. Then the carry output is 0 in case where both the inputs are not 1. And the next, the least significant bit of the sum is defined by the sum bit. From the truth table, we can derive the sum of products expression of the sum and carry. Do you remember how did we write the sum of products expression from truth table? We selected only the min terms that produced 1 and ORed them. Similarly, you can write now. Observe the sum output of the truth table carefully. The sum is 1 when A equal to 0, B equal to 1, and when A equal to 1, B equal to 0. So, the corresponding min terms are A complement B and AB complement. So, logical expression for sum is sum equal to A complement B plus A B complement. The carry is 1 when both A equal to 1 and B equal to 1, and the corresponding min term is AB, and that itself is the expression for the carry. So, carry equal to AB. Now, you can draw the logic diagram as shown here. A and B are two inputs and sum and carry are outputs. Here input A is fed into a NOT gate that produce A complement. Thus, A complement and input B is fed into another AND gate to produce A complement B. Input B is fed into a NOT gate to produce B complement, and this B complement and input A is fed into another AND gate to produce A B complement. The outputs of AND gates A complement B and AB complement are fed into an OR gate to generate the desired output A complement B plus AB complement. This is the sum of the half adder. The carry AB can be produced by ANDing A and B inputs. This is the logic circuit of half adder, the AND/OR implementation of half adder. Notice the expression for sum once again, sum equal to A complement B plus A B complement. Can you recall this expression? This is the logical function of XOR gate. So, some output of a half adder can also be expressed as the exclusive OR of the input variables. Therefore, we write sum equal to A XOR B. Carry output is the same, AB. Now, let us design the half adder with XOR implementation. The inputs A and B are connected to an XOR gate to output the sum, and the same inputs are fed into an AND gate to output the carry. So, half adder can also be implemented using an XOR and AND gate. Hope all different aspects of half adders are clear. The next, we dive into the concepts of full adder. What is a full adder? It is a combinational circuit that performs binary addition of 3 bits. The full adder accepts 3 binary digits on its inputs and produces 2 binary digits on its output, and those outputs are sum and carry. To carry out addition of any two binary numbers, in the first step we just add 2 bits, the least significant bits, and then onwards we add 3 bits, 2 significant bits from those two numbers and the carry from the previous step. So, addition on any two binary numbers can be completed only by performing 3-bit addition, and hence we have a full adder. Logic symbol of a full adder is given here. It is the adder which adds 3 inputs and produces 2 outputs. The first 2 inputs are A and B, and the third input is called input carry. The outputs are sum and output carry, that is designated as Cout. Now let us form the truth table of addition of 3 bits. If inputs A equal to 0, B equal to 0 and C in equal to 0, output sum equal to 0 and carry equal to 0. This is obtained by binary addition. 0 plus 0 plus 0 gives sum equal to 0 and carry equal to 0. If inputs A equal to 0, B equal to 0 and C in equal to 1, then output sum equal to 1 and carry equal to 0. It is obtained by binary addition 0 plus 1 that gives sum as 1 and carry as 0. The next, if inputs A equal to 0, B equal to 1 and C in equal to 0, output sum equal to 1 and carry equal to 0. If inputs A equal to 0, B equal to 1 and C in equal to 1, outputs sum equal to 0 and carry equal to 1. The next, if inputs A equal to 1, B equal to 0, C in equal to 0, output sum equal to 1 and carry equal to 0. If inputs A equal to 1, B equal to 0 and C in equal to 1, outputs sum equal to 0 and carry equal to 1. If inputs A equal to 1, B equal to 1 and C in equal to 0, outputs sum equal to 0 and carry equal to 1. And if inputs A equal to 1, B equal to 1 and C in equal to 1, the output sum becomes 1 and carry becomes 1. Now, let us deduce the sum of products expression for the output sum and Cout using K-map. Draw the K-map for the output function sum. From the truth table, we see that the input values 0, 0, 1, 0, 1, 0, 1, 0, 0 and 1, 1, 1 produces 1 for the sum output. Mark them in the corresponding cells of the K-map. No groups are formed. So, the minimum sum of products expression for sum is A complement B complement C plus A complement B C plus A B complement C complement plus A B C. Then draw the K-map for the output function Cout. The input values 0, 1, 1, 1, 0, 1, 1, 1, 1 and 1, 1, 0 produces 1 at the output carry Cout. So, map the ones, we get 3 pairs and the sum of products expression for Cout can be written as AB plus AC plus BC. Now, we have the sum of products expression for sum and carry as sum equal to A complement B complement C plus A complement BC plus AB complement C complement plus ABC and carry equal to AB plus AC plus BC. Both of these expressions can be implemented using AND OR logic. Let us draw the logic circuit for the sum function. Input A complement B complement and C are fed into an AND gate produces A complement B complement C, where the complemented inputs are generated by using a NOT gate. Then A complement B and C to the second AND gate produces A complement BC. Then A, B complement and C complement to the third AND gate that generates A, B complement, C complement, and the last term ABC is generated using the fourth AND gate. These product terms are fed into an OR gate to get the sum A complement B complement C plus A complement BC plus A B complement C complement plus ABC. Now, the logic diagram of carry, which is equal to AB plus AC plus BC. Draw 3 AND gates with the inputs AB, AC and BC respectively. Then OR the product terms using an OR gate. We get the result AB plus AC plus BC. So, we learned the AND OR implementation of a full adder circuit completely. The next, construction of full adder using half adder circuits. This block diagram describes the construction of a full adder circuit using half adders and an OR gate. In this circuit, there are 2 half adder circuits and 1 OR gate. The first half adder has two single bit binary inputs A and B. As we know that the half adder produces two outputs, that is sum and carry, the sum output of the first half adder will become one of the input for the second half adder, and the carry output of the first adder goes to the OR gate. The second half adder takes two inputs. One is the sum of first half adder, next is Cin. The sum output of second half adder becomes final outcome of the full adder circuit. Its carry is going to be the second input of the OR gate. The output of OR gate is the final Cout, the carry output. We have already seen how a half adder function is implemented using XOR function. Now, this can be easily extended to implement a full adder. See how the sum is implemented. Initially, perform the XOR operation on inputs A and B. We obtain A XOR B. Perform XOR again on this input with carry. It generates the final sum output A XOR B XOR Cin. How do you get Cout, the carry output? Inputs of first half adder are A and B and its carry is AB. What are the inputs of second half adder? A XOR B and Cin. So, carry from the second half adder is A XOR B dot Cin. The logical sum of these two carries gives us the final carry output, that is AB plus A XOR B dot Cin. With this, we completed 2 bits addition and 3 bits addition. Proceeding to the next, addition of two binary numbers having more than 1 bit. A full adder can add two 1-bit numbers and an input carry. To add binary numbers with more than 1 bit, we need additional full adders. For each set of 2 bits, we need a separate full adder circuit. This requirement introduces parallel binary adders. Parallel binary adder is a digital combinational circuit capable of finding the arithmetic sum of two binary numbers whose length is greater than 1 bit. These numbers are added by operating on corresponding pairs of bits in parallel. Before discussing more about parallel binary adders, let us just recollect binary addition of two numbers. There are 4 rules that needs to be followed when adding two binary numbers. They are 0 plus 0 equal to 0, 1 plus 0 equal to 1, 1 plus 1 equal to sum 0 carry 1 and 1 plus 1 plus 1 equal to sum equal to 1 and carry equal to 1. And we know that logical addition is commutative. For example, let us add two binary numbers 100101 and 101011. The least significant bits of the number 1 and number 2, that is 1 and 1, are added first to get sum equal to 0 and carry equal to 1. This carry is forwarded to the next column to the left. While adding second column from the right, 101 are added to get sum equal to 0 and carry as 1. While adding third column from right, 110 are added to get sum 0 and carry 1. While adding fourth column from right, 101 are added to get sum 0 and carry 1. While adding fifth column from right, 100 are added to get sum 1 and carry 0. While adding MSB 011 are added to get sum 0 and carry 1. In each step of addition, we find the function of a full adder. Exactly in the similar way, we implement parallel binary adder. So, what is a parallel binary adder? Full adders connected in a chain where the output carry from each full adder is connected to the carry input of the next higher order full adder in the chain is known as parallel binary adder. An n-bit parallel adder requires n full adders to perform the operation. The least significant bits can be added either using a half adder or using a full adder with Cin equal to 0. We consider a full adder for the same. So, for 2-bit numbers, 2 adders are needed. For 4-bit numbers, 4 adders, and so on. This is the logic diagram of a parallel binary adder. As shown in the figure, firstly the full adder FA1 adds A1 and B1 along with the carry C1 to generate the sum S1, and the carry, say C2, is connected to the next adder in chain. Next, the full adder FA2 uses this carry bit C2 to add with the input bits A2 and B2 to generate the sum S2, and the carry C3, which is again further connected to the next adder in chain, and so on. The process continues till the last full adder FAN that uses the carry bit Cn to add with its input An and Bn to generate the last output bit Sn along with last carry bit Cout. Hope it is clear. There is a serious drawback with parallel binary adder. It is the delay that increases linearly with the bit length. As mentioned before, each full adder has to wait for the carry out of the previous stage to output its result. Therefore, even if the adder has a value at its output terminal, it has to wait for the propagation of the carry before the output reaches a correct value. FA2 has to wait for output from FA1, FA3 needs to wait for output from FA2, and so on. This is to be rectified for increasing the processing speed. We will come to that in a later session. So, let me summarize the concepts we went through. Half adder is a combinational logic circuit to perform binary addition of 2 bits. If A and B are 2 input bits, sum is obtained by performing XOR operation of A and B and carry by finding AND operation of input bits A and B. Full adder is a combinational logic circuit to perform binary addition of 3 bits whose sum is obtained by Boolean expression A XOR B XOR Cin and carry obtained by the expression A dot B plus A XOR B dot Cin. We also have seen parallel binary adder, which is a digital combinational circuit capable of finding the arithmetic sum of 2 binary numbers whose length is greater than 1 bit. It is implemented using full adders connected sequentially. With this, I conclude the session. Thank you for watching. See you in the next session. Bye.